So sometimes it's also referred as quantitative structure SPR. Tak pasti saya rekod je dah dulu. Mana rekod.
Recording in progress.
Okay. So I just used the slides from Bashar because saya memang tak ada slide ni. Okay. So this is, for example, a design cycle for designing new drugs, or you want to produce new drugs. So you have this kind of cycle, right? Where you have several steps involving before the drugs can be orang kata apa, test, clinically test, belum production lagi. So now before untuk produce new drugs tu you require like hundreds of millions, right, of US dollar, for example, to create just one new drugs, for a pharmaceutical company, right? So the traditional way of producing new drug is basically you have your biological concept or your biological activity yang you nak approach, right? For example, like you want to reduce the activity of a certain enzyme that can cause, for example, rheumatoid arthritis ke. Rheumatoid arthritis can be can be amplified by the synthesis of PAD4 proteins and such as like that lah. So if that is your target protein, then you need some compounds that can reduce the activity of the enzymes. So something like that, right? So before Qsar, you have one or two potential compounds, but it's not working enough, and you need more potent compounds. Then if it's like one or two biological activity can be produced from like 10,000 of compounds, right? Has the potential of giving that biological activity. So you need to reduce that in order to get your the most potent one, and then if you were to do that by trial and error, maknanya every compound need to be synthesized, every compound need to be tested. So if you have 10,000 of compounds, you will most likely require 20 or 30,000 of rats, mice to kill with that compound. Kita try lah kan. So it require a lot of time and a lot of money. Okay. So that's where Qsar come in, or drug screening come in. We screen those 10,000 of compounds into hundreds or 10 or 20 or 50 compounds, right? So you have if you look at this chart, you have your biological concept, and then you have this concept that all the biological activity and you not observe, then you use computer aided lah. You use computer to help you lah. So for example, obtain the protein, obtain the structure of the compounds, or design new compounds. And the de novo design means you design a new, right? You design new compound, literally never be synthesized before, right? But the problem with new compounds or new leads, it requires designs of the series designs or synthesis design. Synthesis design means some compound might not be synthesized before, so you have to figure out how to synthesize it. That takes a lot of time also. You have to optimize juga untuk dapatkan high yield and so on, right? So you have these lead structures that you can do series design and synthesis design, and then you go to synthesis, right? So without Qsar, this would be for 10,000 of compounds lah, sampai biological testing. Okay, so dekat situ memang lama lah. So when you have Qsar, you can reduce the number. So basically, we want to reduce the time, we want to reduce the money, the cost, right? So what would you do with the Qsar is that you find several distinguished compounds and then you synthesize it, test for biological activity, and then use that compound as orang kata macam standard or reference lah. Okay, and then these other thousands of molecules, then we screen with structure activity relationship or Qsar lah. Okay, so by doing that, we eliminate the compounds that cannot fit the profile of providing good biological activity. Macam mana kita tahu? Because kita dah synthesis and then kita dah ada kita punya parameters yang kita nak tengok. Then bila kita dah ada equation, okay. So kat situ penting perkataan equation because this is quantitative, right? Quantitative mean you use mathematical, right? So this is a mathematical relationship between the structure and the activity. So Qsar ni is relate directly to biological activity lah, right? That's why Qsar. That's why ada juga QSPR. QSPR is when you don't look at activity, you just look at physical properties. Then we call QSPR lah. Right? When you call it Qsar, then this is usually used by medicinal chemists or pharmaceutical company lah untuk design drug lah. So dia akan guna quantitative structure activity relationship. But sometimes this Qsar, QSPR ni dia intention dia punya usage tu dia interchangeably, dia macam bertukar-tukar. Tapi it means the same thing lah. The method is quite the same. It's just what the thing that we want to observe lah. For example, Qsar is more on activity lah. Okay. So what Qsar does is shorten the cycle and reduce the number of candidates so that you don't have to synthesize thousands of molecules. Instead, you just synthesize like 40 to 30 compounds and do biological testing lah. And then when you have biological testing done, you will find the candidates for further drug development lah. So this is we call the investigational new drug where dia dah ada lepas pergi kepada animal, dia akan pergi kepada human trial. Human trial tu macam ada group yang placebo, ada group yang dapat drug, and dia akan test efficiency, effectiveness and so on, side effects, everything. Then only dia become new drug. And this process does not stop here. This process still have to go through safety, federal approval, ministry approval. Kalau kat Malaysia ministry approval lah kita panggil. Kalau kat US dia panggil FDA approval. So Food Drug Association and then after that baru keluar new drug, right? So when the new drug comes out, basically the company that developed that drug, it holds the patent lah for that drug. But it can hold the patent for that drug, I think, for just like 7 years, right? And then after that, other companies can also synthesize that drugs, which is good, and became a generic drug lah. Macam paracetamol kan, dia ada banyak jenama, ada Panadol, ada Euphamol, so because dah jadi generic drug lah. Okay, so that's why nama drug tu lain tapi compound dia sama. Okay, so it's still the same drug but with different name lah bila dia dah jadi generic drug. Okay, so this company would really like macam ada orang, macam mana saya nak admit? Macam ada dekat waiting room tadi. Okay, so they need fast development. For example, you require like 10 years to get a new drug, but you hold that new drug for just like 7 years to make a profit, right? To make a big profit lah. Okay, so you need a faster way to design new drug lah. So this is from the company's view lah. Bukan kita lah, kita lagi suka lah kalau lebih banyak company sell the same drug, then the price would be lower. Okay. Alright, so Qsar attempt to identify and quantitate physicochemical properties. So this is also important of a drug in relation to its biological activity. So these parameters are orang kata physicochemical properties such as hydrophobic, and then electronic properties also, steric properties, whether it's a whole molecule or pieces. So usually for Qsar, simple Qsar, dia a part of molecule sahaja. Kita ada macam scaffold. You ada scaffold, for example, you have an aromatic ring, you have a scaffold, and then you test with different different substituent lah. Boleh saya you ada macam a benzene ring as a scaffold, and then you can test with for example here X, right? So you can test different X, find the perfect X lah, kalau boleh perfect lah, find the perfect X to attach to the benzene ring in order to make it more useful or potent lah, potent drug, something like that, right? But if you have like a 3D Qsar, which is the advanced Qsar, you have a 3D, three-dimensional, then it usually involves the whole molecule. It requires the information on the geometry, the stereo specificity, dia punya stereo bond dia, and dia punya plane, and then dia punya also is electronic properties juga lah. Okay, so the real advantage of Qsar is that you don't need too many compounds made lah in order to test, so it reduce the numbers lah. Itu basically screening lah, perkataan yang paling tepat sekali untuk Qsar ni ialah when you have to do drug screening. Bila kita nak buat drug screening, Qsar is one of the option lah, right? Rather than you nak buat molecular docking on 10,000 of compound, you can just do molecular docking for hundreds of compound. So maybe do Qsar first before you do molecular docking. That way you can reduce the number of try and error. Okay, so what we come out with Qsar is an equation that describe the relationship between the activity or biological activity yang kita nak dengan descriptors. Kita panggil dia descriptors, tapi dia sebenarnya macam properties lah, properties yang kita nak tengok. So there are several properties that can contribute to the activity of that compound. So this is what we call the descriptors lah. Okay, so the relationship between the activity and the descriptors, we have that equation, and then we have samples lah of compound. Then if it fits the equation or it gives the equation gives good result for that compound, then that compound is basically potentially a drug candidate lah. Okay, however, please remember that this is prediction. Since this is computational, it's prediction, you still need to go to the lab and synthesize and then test. Okay, sometimes the result is very good, that it is orang kata apa, macam too good to be true. So it requires also at the final stage, after you get the Qsar result, maybe you need also your chemical intuition in order to see how come this drug is good, sedangkan dia ada this kind of functional groups and so on. So you have to not trust the computational result 100% lah, because computational result is basically prediction. Okay, so if the standard compound, ini standard sepatutnya, if the standard compound or the reference compound does not fit the equation that you get from Qsar, then basically you need to modify the equation lah. So you need, macam saya cakap tadi, first you have to synthesize several dulu, dapatkan dia punya experimental result. When you have experimental result to compare, then you can get a good Qsar punya equation lah. Okay. Oh, dia tak hilang ni. and then nak dapatkan value R squared yang dekat dengan 1. You need to get a R squared value that close to 1. If it's too far from 0.9 something, then in medicine dia tak terima lah, right? So you need your graph tu. So it's a statistical method lah. Pretty weird way to do chemistry lah, but yes, it works. It works actually, right? So you have biological activities, right? So that is most often expressed by logarithm and molar activities. So these are structural elements punya contribution lah. Okay, so you have like free will set analysis, hunch analysis, or 3D Qsar lah, macam saya cakap tadi, in which 3D Qsar ni dia pakai force field lah. Apa tu force field belum sampai situ lagi ya. Okay, so macam saya beritahu tadi, if you do classical Qsar analysis, you consider only 2D structure, and sometimes most of the time is only a part of that molecule. Macam saya tunjuk tadi yang X tu je, kita tengok dekat situ je. Okay, but for 3D Qsar, Qsar ni actually one of the earliest 3D Qsar. Ada banyak lagi, sekarang ni ada banyak, ada masalah. So this is one of the earliest lah. Qsar ni basically siapa? Kramer yang buat lah. So based on steric of a 3D size of the molecule, geometry, shape, and so on, right? So you have two types lah. If you do 3D Qsar, it's basically it should be better lah. It should be better because it incorporate more properties lah, instead of just 1 or 2 dimensional, and it becomes 3 dimensional now. Okay. Alright, so these are some basic requirements in Qsar studies. Right, so all analogs must have some general features yang dia sama. Right? So all analogs ni, kalau contoh, dia mesti ada at least satu benzene ring. Okay, so cuma dia punya substituent pada benzene ring tu saja berbeza. That mean mesti ada something yang dia similar. Okay, supaya kita dapat eliminate that. Senang kita nak eliminate dia punya contribution of the other part of the molecule. So you don't need all parts of molecule, you need just 1 or 2 parts of the molecule saja yang you not observe. So when you have some one scaffold, then that scaffold mesti semua molekul tu mesti ada scaffold yang sama macam yang tu. Okay, so all analogs can exert the same mechanism of action. Kita assume dia exert same mechanism of action, whether dia by esterification ke, whether dia SN1 reaction ke, SN2 reaction ke, right? So it must have same mechanism of actions. Bind in a comparable manner. This is when you ada banyak sampel dan you nak dia semuanya cara dia attack the target is the same, right? So if you replace something, then it will loses the same electronic properties, right? Same electronic properties, so dia kata isosteric tu, right? So it can be predicted lah, right? And then the last two ni bila you involve docking lah, bila you involve docking to the Qsar punya ni, bila you incorporate docking into Qsar lah. So your binding affinity is correlated to interaction energies, because biological activities tu memang they correlate with binding affinity lah. Okay, so how good the compound bind to a specific target, that means that how good the drug bind to specific target lah. So kalau binding affinity dia tinggi, it means that it is a very highly potential drug lah. Alright, so involve the derivation mathematical formula, dah cerita tadi, relates biological activities. Okay, so these parameters have major influence on the drug activity. So these parameters ni sebenarnya dalam slide ni tak ada sebut sangat. Kita panggil dia juga sebagai descriptors, right? Molecular descriptors. So keep that in mind lah. Right? Bila saya sebut molecular descriptors tu maknanya is a parameters yang dalam Qsar punya equation, right? So this is general form ni, in purple words, purple fonts ni, right? Prof Basha memang suka lah warna purple ni, right? So biological activity is the one that we want to observe, the one that kita nak target, right? Whether dia reduce the activity of the enzyme ke, whether dia have lower the activity of the infected part of the cell ke, macam tu lah, right? So the function is the one that we want to determine, right? The parameters is the one that we set, which parameters contribute to the biological activities, such as log P, for example, log P is a partition coefficient punya parameters, then you have like steric, and then ada banyak lagi lah basically. Saya rasa ada table sekejap lagi. So activity is expressed as log 1/C, right? So basically C is the minimum dose lah, minimum dose, right? Minimum concentration required to cause a defined biological response, means that some kind of dose lah, so activity usually expressed as log 1/C. Dia terus ke sini. Okay. So these are the orang kata apa, some of the parameters lah. For example, chemical properties, you can look for pKa, you can look at partition coefficient, solubility, stability, right? And then intrinsic properties ni macam Hammett's constant nanti, such as molar volume, connectivity, charge distribution, molecular weight, polar surface area, and biological properties, so activity, toxicity, biotransformation, pharmacokinetics. So these are the correlation lah. One molecule can have like different pKa, and then this contribute to the different toxicity, and then also it can has like high molar volume and so on. So these are the relationship lah. Okay, so these are the most common parameters used in Qsar. You have electronic parameters, right, such as the Hammett's constant, lipomolar. We'll get to Hammett's constant shortly, right? Lipophilic parameters, so lipophilic parameters ni Hans punya ni lah, parameters ni, such as log P lah kat sini, log P. Log P ni basically how well the compound can break through the membrane of the cell, right, into the fluid, into the okay. The pi substitution constant, right, steric parameters or the Taft constant, polarizability, and miscellaneous parameters. Ada table kat sini, kat sini lah. Okay, so you have parameters such as hydrophobic, and then this one, yang penting, some of the parameters at least must be able to be measured experimentally. Itu penting juga, right? So parameters apa yang you nak masukkan dalam you punya Qsar punya equation. Remember, Qsar punya equation is generic. You need to create your own equation, right? Your own equation. So from your own equation, you nanti bila you masukkan semua compound punya value for each compound, you akan dapat value for each compound. For example, atomic net charge, right? So you have thousands of compound, you calculate the net charge for each compound, and then you masukkan value tu dalam you punya equation yang you design, right? So and then you masukkan juga partition coefficient, the log P value of that compound, and then you masukkan juga solubility parameter dia, and then you masukkan juga molecular weight dia, then you masukkan juga dia punya Hammett's constant, and then Taft constant, right? So when you have all these values, you get your 1/C, right? Log 1/C tu. Because you masukkan dalam equation ni tadi, equation yang you buat. Nanti akan tengoklah beberapa equation yang ada lah. Okay. So bila you dapat this value, you akan plot. Kalau you nampak ada graf kecil yang line hijau kat bawah ni, right? You akan plot dia, regression plot tu. Bila you ada regression plot ni nanti, you kena match dia dengan the ones that you synthesize and determine experimentally at the lab, right? So kita tengok dia punya correlation. Kita akan calculate dia punya R squared. So if the R squared is close to 1, 0.9 and above, then it will be a very good correlation. Then you know your Qsar model works perfectly lah. Not perfect lah, perfect mesti satu lah, right? Ada punya correlation dia. Okay, works very good lah. Kita boleh cakap macam tu, right? So you need your R squared to be as close to 1 as possible, right? So that's what you get lah. Bila you ada banyak value log 1C tu, because you dah masukkan semua parametersnya dalam equation, dan you calculate for each compound, and bila you plot, you dapat regression plot yang cantik, then basically your Qsar model is good lah, very good. Okay. So these are the some of the parameters can only be calculated like theoretically, right? Macam you kena calculate dia using computer lah. For example, highly occupied molecular orbital dengan lowest unoccupied molecular orbital ni, homolumo ni, ini kena guna quantum mechanics lah kalau you nak calculate ni. Contohlah, electrostatic potential, maybe you can guna quantum boleh, you nak guna molecular mechanics pun boleh, but you can determine this computationally. Log P juga you boleh determine computationally, and then you have you can also determine experimentally using octanol and water. We will show you later on. Okay, so some of this, for example, you can get by not doing synthesis. Okay, it's important that you can get these parameters or these descriptors yang you nak observe dalam you punya equation, yang you nak include dalam you punya equation. Lebih banyak yang boleh dikira melalui computational chemistry, then is better because you don't waste time to go to the lab to do experiment, or it is available in literature or in database, and that would be most orang kata apa, the best case scenario lah. The best case scenario is that for all the compounds or all the samples, sample of compound, for example, if you have like 100 compounds, so these 100 compounds, you have the data sets for it for like 3 or more orang kata apa, descriptors, and then it will make your job a lot more easier lah. Okay. So we look at descriptors now. The first one is the Hammett's electronic, right? So this is a substituent constant. Kalau kita tengok kat sini, dia ada kat sini. Electronic descriptors, which is the Hammett constant. So this is also involved in the Qsar model. Okay. So the measure of electron withdrawing or electron donating influence of the substituent. So dia hanya tengok bila you replace substituent saja. Bila you replace X. Okay. So if X is H, then KH or the dissociate constant equals to this equation lah. Patut ini you kena ingat lah ni, ini acid base equilibrium ni, right? So bila you dapat constant untuk H, and then you tukar, right? And you tukar, and then you tukar lagi, and then you tukar lagi. So each time you tukar, basically you test different compounds lah, right? Bila you ada 1000 compounds, you kena tukar 9,999 kali lah. Tapi itulah, dekat situlah komputer datang membantu lah. Dekat situlah software membantu. You just perlu listkan saja dia punya compound, masukkan je nama compound dalam you punya apa, Excel ke, and then you export the Excel file masuk dalam you punya software, software baca compound apa yang nak, make sure ada dia punya 3D structure or 2D structure, and then dia akan kira sendirilah. Tak perlulah kita satu-satu kita nak replace yang kita kira, sebab kita guna komputer, so it should be faster, significantly faster. So it will measure the electron withdrawing or electron donating effects compared to benzoic acid, right? Inilah benzoic acid ni. Kalau benzoic acid macam dia kira sebagai nombor satu lah, benzoic acid, and how it affect its ionization lah. Okay. So example diberi kat sini lah. Example diberi kat sini, kalau you guna NO2, you replace X dengan electron withdrawing substituent, right? So the position of equilibrium moves to the right. Okay, so the KX would be higher than the K benzoic acid lah. Macam tu. Okay, so these are the equation. I think tak perlulah kita fokus dekat sini. Yang penting kat sini nak tunjuk macam mana cara dia. Okay, macam mana cara nak dapatkan constant tu, right? So you change this to some kind of group. Kat sini contoh diberi ialah NO2. right? So you change the X from hydrogen to NO2, and then apa tu? Dia akan bagi you basically reaction yang sama, cuma dia punya equilibrium dia move to the right. Okay. Why? Because charge is stabilized by the NO2, so equilibrium will shift to the right. So this is basically what you observe lah bila you tukar, right? So this the value will be given lah. Okay. Right. So if you add electron donating substituent such as a methyl group, then the position of equilibrium moves to the left, right? And charge is destabilized by the methyl group, right? Because the electron goes towards the ring, not outside of the ring. So it disturbs the delocalization of the pi electron S2. So your new dissociation constant tu akan kurang daripada dissociation constant yang asal. Okay. Right. So usually electron donating group ni ialah alkyl group lah. Alkyl group. Right. Another example kat sini position of your substituent. Right. Ini position. Kalau you letak dekat NO2 dekat para, ini value dia, dissociate apa dia punya Hammett constant dia. Kalau you letak dekat meta position, ini value dia. So different position juga akan bagi you different value. Okay, different position juga bagi different value. For example, like electron withdrawing ni, usually dia duduk dekat meta dia because dia naturally dia akan pergi dekat meta lah. But you can force it to go at para also. Para position tak ada dia tak pergi dekat auto position. Tapi still you boleh kira. Kalau you buat computational, usually you boleh kira, tapi dia akan kira sebagai invalid lah, because the group the group is quite big lah, right? So this is electron withdrawing, ditunjuklah kat sini contohlah resonance effect based on the electron withdrawing punya substitution. Okay, so yang ini OH is electron withdrawing juga. Yeah. Okay, so electron donating by terus saya rasa macam electron donating OH kenapa ni keluar juga. Oh, okay. So dia tukar dekat sini ialah OH. Okay, so the drug, if you electron donating, right, so dia akan ditunjuk benda yang sama lah. So kalau dia dekat meta position 0.12, kalau dekat para position negatif 0.37. So give sort of different value. You don't have to worry about calculating or determining whether dia punya value akan naik atau turun. Yang you kena faham ialah there are two types. First, you can replace and you can change the position also, right? So that is for the substituent constant or the Hammett constant lah, basically. The Hammett constant lah, denote by the symbol sigma. Kalau jumpa dalam Hans equation lah, basically tak juga, sebab sekarang dah tukar. Kalau you lihat dalam you punya Qsar model ada lambang sigma ni, maknanya this is the substituent punya descriptor lah. Hammett constant punya descriptor. Okay, so basically electron distribution effect on the compound, electron distribution effect on the compound. Now we look at the hydrophobicity or lipophilicity effect of the compound. Okay, kalau compound tu partition coefficient dia tinggi, then basically dia senang untuk senang untuk tembus dia punya membrane cell. Itu yang penting kat situ, kenapa famous sangat log P ni, sebabnya bila you ada drug, for example you nak buat transdermal drug, bukan yang oral drug, you nak drug yang sapu, you nak yang sapu, it basically have to penetrate your skin, right? Or kalau even you ada drug yang oral pun, you still need to penetrate the membrane of the cell in order to go to the example target protein. You ada protein yang you target tapi dia duduk dalam sel, dia ada dalam membrane yang besar. So you need the drug to be able to travel through the membrane lah. Okay, so that's why partition coefficient ni agak famous lah. Okay, So experimentally, you can observe this by using octanol and water. Octanol and water, you have your compound, you calculate the partition coefficient in octanol and water. So basically, you get log P. Okay, you get log P. Kita tak tengok distribution coefficient tu, jadi kita tengok partition coefficient sahaja. Right? So when you have your I tak tahu kenapa graf ni kat sini. Yang ini ialah you punya hasil daripada you punya Qsar model. Kalau ini contoh, kalau Qsar model you involve hanya log P lah ni. Kalau you tengok graf ni, and this is your Qsar equation. Log 1 over C equals to 0.75 log P plus 2.30. Macam tu, right? So plus 2.30, kalau tak silap saya, this is the apa tu dia punya apa? Dia punya intercept kat sini. YMX tambah C kan? You punya X is log P, right? This is 0.75 with your M, right? This is your Y, right? So basically it's a linear graph here. Okay, and you have your experimental data, right? Bila you combine dengan experimental data and then you calculate your R squared, make sure that you need to get close to 1. Okay, so binding will increase as log P increases, is greater for hydrophobic drug. Of course, hydrophobic drug akan lebih senang untuk tembus skin because our skin is hydrophobic, right? So membrane pun usually they are hydrophobic, right? So that's why they guna octanol kat sini, because octanol ada compound. Octanol kalau you lihat dia ada chain alkyl chain yang agak panjang, which is 8 carbon kan, and then dia ada one part which is hydrophilic part. Right, so this hydrophilic part is faced towards the water lah, right? It's faced towards the water. Water is hydrophilic, so dia akan jadi macam layer, right? Dia akan jadi macam layer. So if your compound can travel through these layers easily, that means your compound will have a high log P value, right? It has a polar and non-polar region. The log P octanol over water is fairly easy to measure, often correlates well with many biological properties, can be predicted fairly accurately using computational model. Macam saya cakap tadi, log P ni kita boleh calculate using computer boleh, using apa tu, experimental pun boleh lah. Okay, so penting lah untuk kita dapat correlation, right? Tak boleh dapat data daripada computational punya calculation and then you just take it macam tu je, tak boleh so you have to validate juga, kena validate juga. Alright, so the way to calculate log P for this is basically concentration kan, concentration of octanol, concentration of water, and then the log P values. Okay. So if graph extended to very high log P value, it becomes a parabolic curve lah. So the reason might be to poor soluble in the compound might be poorly soluble in aqueous phase, trapped inside fats, and then more susceptible to metabolism lah. So this is a Qsar equation. Example again, dia bagi lagi Qsar equation. You ada dua log P kat sini. One is log P squared and one is log P lah. Okay. So P small dominated by log P, P large log P squared dominates, and so activity decreases lah. So this is another example of a Qsar model based on log P sajalah. K3 ni is the intercept of the regression tu lah nanti ya. So yang ujung ni dia ada value saja, dia tak ada dia punya ni. Okay. Alright, so this I think this is an example lah. General anesthetic activity of ethers. Okay, so again you have your values here, 0.22 kat sini masukkan, 1.04 masukkan lah, right? So and then you calculate your log P for each of your compound, right? Masukkan je log P of each of your compound, then you get your log 1C. When you have your log 1C, you plot the linear graph tu. Plot the linear graph tu lah. Okay. Alright, what is poor bioavailability? Compounds that are too polar that will not partition into membranes in the first place. Compounds that are not polar enough cannot partition back out. So there are two types of poor bioavailability lah. whether dia tak boleh masuk langsung ataupun dia masuk tapi dia tak boleh keluar. Okay, so this is one of the case lah yang you akan jumpa lah. This is example lah actually. Okay, tak semestinya you dapat compound yang macam ni, but in case you plot your log 1C over log P, somehow you get a parabolic curve macam ni. Somehow you get a parabolic curve. It means that the first compound yang duduk sebelah sini ni, compound yang duduk sebelah sini dengan duduk sebelah sini, it has poor bioavailability. So what you do when you have log 1C gram macam ni, you cut lah compound yang duduk sini dengan compound yang duduk sini, keluarlah daripada you punya senarai candidate, right? Keluarkan dia daripada senarai candidate, so you get less and less numbers of compounds to look at. Okay, what else does log P affect? If the log P increases, binding to enzyme receptor also increases. Okay, if if log P increases, it has low aqueous solubility. If log P increases, binding to P4550 metabolic enzyme, I think this case only for P450 metabolizing enzyme. Okay, so absorption through membrane is high because bila log P tinggi, hydrophobicity pun tinggi, maknanya dia senang nak tembus membrane. Okay, binding to blood tissue protein, less drug free to act, and so on, and then binding to HCRG high ion channel, kind of say example. Okay, so log P needs to be optimized. For your drug, untuk dapat candidate drug tu mesti log P tu agak penting lah. That's why they're very famous lah. Untuk dapat in drug design, people usually tend to first look at log P. Itu tak considered sebagai a drug candidate because log P dia tak bagus, then what for kan? So because nanti whether dia boleh bind kat protein is a good thing, tapi dia tak boleh sampai kat protein, right? Dia tak boleh sampai dekat you punya protein yang you target tu, tak boleh juga, right? No use, right? Alright, the log P measures the drug overall hydrophobicity and measures the drug transportability. So whether they're very hydrophobic and whether they can move through membrane easily lah. What is pi? Pi measures the hydrophobicity of a specific region on the drug. Okay. On drug. So hydrophobic bonding to tambah because you ada dua substituent kat situ, you tambah, right? Kalau yang macam ni you observe, you dapat terus value dia, right? Because you calculate the concentration experimentally macam ni, right? Macam gambar ni dalam beaker, ada dua layer octanol and water, measure solubility dia. Tapi kalau you guna theoretically, then you have your benzene already reported one ataupun ada dalam database, and then the value of pi for Cl yang ada dalam database, and then the value of pi for the amide yang ada dalam database, then you tambah all together, you dapat you punya overall yang you boleh compare dengan experimental. Tapi kat sini ada beza jugalah, 1.35 dengan 1.51. Okay. So this are example a big molecule kat sini, right? So you want to, for example, you ada satu molekul, then make sure that you identify the substituent ataupun dekat mana yang you nak kira dia punya apa tu, contribution, right? Dia panggil contribution. So first you ada you punya fragment yang warna merah tu, 3,5-pyrazolidine-dione, right? So then you ada you punya parent, then dia ada branch kat situ, dia pecah branch dia, and then you calculate for the branch, you have 5 carbon, right? 5 aliphatic carbon, These 5 aliphatic carbon contributed 0.975. The fragment one contribute minus 3.24. These are the value log P dia lah, right? The value log P ataupun kita panggil dia value pi dia tadi. Value pi dia. Okay. And then you ada carbon daripada 2 benzene ring ni, right? You ada carbon daripada 2 benzene ring ni, 12 aromatic, right? So overall contribution 1.560 tambah semua lah, right? Contoh kalau bahagilah, dibahagi 12 you dapatlah untuk satu carbon aromatic. Okay, so basically branch yang satu branch minus 0.13, and then you have another 3 chain kat sini, right? Allylic, tapi sebab dia nak tunjukkan dia punya contribution tu sama, right? So that contribute to 0.540, right? And then you ada hydrogen, 20 hydrogen, right? On the isolated carbon 4.540. Basically tambah semua ni, you dapat C log P. What does C log P means? C means calculated lah. Okay, selalunya kalau you guna software, dia akan bagi you value C log P. C log P tu maksud dia ada calculated log P. Calculated log P. So tambah je semua ni, tambah je semua, and then you get lah you punya log P. Dekat sini ada correction. Mana correction dia? Ada correction. So this one, this just tambah, right? Okay. Tadi itu mula you dah tengok Hammett. Hammett is the Hammett constant, electron distribution, and then you tengok Hunch, which is the lipophilic properties, and now kita tengok Tough. So dia ada 3 lah, ada 3 orang, nama dah keluar 3 nama dah, right? Hammett, Hunch and Tough lah. Hunch ni dia famous lah dalam Qsar, memang dia famous lah, dia macam founding father of Qsar lah, Hunch ni, right? So what Tough contribute, right, towards the Qsar is by including the steric substitution constant, right? Steric means bulky lah, the bulkiness of the group. One carbon, what happen if you replace that substituent that has 1 carbon with the substituent, similar substituent but with 2 carbon, but with 3, 4, 5, 6 carbon. So dia makin lama makin besar, dia punya steric effect dia increase, right? Itu yang kita nak tengok lah, whether you perlukan substituent yang lebih besar untuk improve you punya overall log 1C tu, right? Kita remember kita punya target is the log 1/C, right? Sekarang ni kita pilih descriptors, kita sedang memilih descriptors and kita sedang optimize kita punya descriptors. So whether or not one of the descriptors must be include steric contribution, right? So steric ni maknanya whether if you replace the compound with bigger and bigger and bigger substituent, what happened to the dia punya steric value dia, steric factor dia lah, right? So this can contribute to the molar refractivity measure, and then value steric parameter. This basically a computer program, right? So you calculate bond angle, van der Waals radius, and bond length. So you can also get steric substitution constant from calculation, theoretical calculation. Okay, and for experimental you can use molar refractivity. Okay, so these are the steric factor. Kalau lihat di example kat sini, ES, log Kx minus log Ko, where the Kx is the rate of hydrolysis of the substituted ester and Ko is the rate of the hydrolysis of the parent ester. So dia punya steric factor ni bila you tolakkan, yang you ubah dengan yang asal, okay? Yang you ubah dengan yang asal. Mula-mula you tengok the rate of reaction for the original one, right? Base, right? Base dengan acid ni, right? Basically you nak calculate satu dulu, tak semestinya ester. Ini contoh, right? You kena ada reaction lah. You kena ada reaction yang you target. So you calculate the rate of reaction for your base compound, and then you change the substituent, right? If you change from 1 carbon to 2 carbon, from methyl you change to ethyl. So what is the ES, right? So calculate that, and then it's not that whenever you want to do Qsar you have to calculate that, but that is the way that people get all this data to form very large database lah, which in our case kita untung lah kalau kita tak perlukan buat yang baru, kita just pakai apa yang orang dah publish lah. So that's one way to look at it, right? But this is how it is calculated, right? So you have your base compound, you calculate the rate of reaction for that compound, and then you change something on that compound. So basically you need a bigger one lah. Ataupun selalu you akan start dengan tiada dulu, then you tambah satu, ataupun ada methyl, you tukar dia jadi ethyl, and then you calculate dia punya ES. Okay. Right. Ini basically ada substituent volume lah. Kalau tadi you tengok by reaction, yang ini you tengok by the volume. Okay. Right. Apa ni? Steric parameter, so you can calculate it using the software ni, ada Sterimol software ni. I tak sure whether dalam punya practical akan guna tak, not sure. Right. So it gives the dimensions of a substituent, and it can be used for any substituent, which is very nice, right? You can use for any substituent, means it's not limited to certain compound saja lah. Okay, so measure computationally lah, basically. Apa yang dia nak bagi tahu dalam slide ni is that you can also measure steric factors computationally. You can either use molar volume, or you measure using berlook steric parameter, ataupun you boleh measure experimentally using the reaction rate, and then you get ES pula, right? Alright, so okay, last part for this lecture for hari ni lah, kita akan tengok sikit pasal Hunch analysis. Drug action can be divided into 2 stages. First, you want to transport the drug. Okay, whether through the skin or orally, inject dalam, okay. So that is one way orang kata apa, kita nak tengok dia, right? So transport. And the other one is binding. Whether bila dia dah masuk, bila drug tu dah sampai dekat dia punya receptor or the target, whether it can bind strongly or not. But that is important also, right? So ada dua benda yang penting lah. Your drug must satisfy both of these first. Then kita kena lihat juga nanti toxicity dia. Kalau kat Malaysia halal ke tak kan? So something like that. Okay. But the first two, whether the drug is deemed to be effective or not, is whether it can be transported easily or whether it can bind strongly. Okay, so kalau it can be transported easily and it can bind strongly, then basically you get a good candidate lah. You get a good candidate, right? But these properties depends on the physical and chemical properties, and then the sign. So this basically Hunch analysis ni when you want to compare your log 1C with your data lah, right? So you punya R comparison must not goes too far from one, or in this case dalam slide dia kata tak boleh terlampau kurang daripada 0.9, 0.9. So kalau you R value dapat R squared, R squared. Kalau you, so it should not differ much. Kalau terlampau macam 0.8, 0.89 okey lagi, 0.85 ke okey kot. Tapi kalau dah 0.80, 0.81, 0.7, then the equation is you need to improve the equation lah. Or maybe you don't have enough samples. Maybe not enough samples. Or maybe bila you buat you punya contoh modeling, waktu you nak buat modeling, nak dapatkan dia punya refractivity ke, maybe you ada salah method kat situ. So itu banyak kerja lah. So hopefully bila you buat, the biggest hope is that your R squared is close to 1. Okay, right? So you have your Qsar equation log 1c be tough constant, and then you have your apa ni overlap apa dipanggil kalau dia tembus axis tu, dia cross axis tu saya lupa. Okay, right? So you have your ni lah, this is basically a complex version of y equals to mx tambah c punya equation lah, linear punya graph tu. It's a complex version because you dah ada lebih daripada satu x. You ada lebih daripada satu x. Okay, y dia still satu, y dia still log 1 over c. You punya c pun you punya apa tu yang apa cross value dah banyak kat sini. Bila x dia banyak, dia punya you have your y and your x, ada dua kat sini, right? You punya apa tu substituent yang you boleh tukar, right? So dia punya equation dia log 1c over sama dengan log 1 over c, which is your activity yang you nak, right? C, remember C is the minimum concentration or minimum dose for your drug, right? So this is what apa tu siapa nama dia, Hunch ni, Corey Hunch kot nama dia, saya tak ingat, maybe lah, tak silap saya Corey Hunch lah, right? What he wants to find before he develop Qsar, dia punya motivation dia is that he wants to find the minimum dose needed for a particular drug in order to be as efficient as possible lah. Maknanya you tak perlu dos yang berlebihan untuk dia jadi efektif. So contoh 500 mg of paracetamol is enough for fever. Right, so tak perlulah sampai 650, and maybe 650 is not for fever, it's for headache and something like that. So you need just minimum dose supaya tak perlulah membazir, and satu lagi maybe overdose is not good lah kan, kita pun tahu. So what he wants to find is the minimum dose. So kat sini that's why they create the log 1c equation lah. So this is his equation. You have pi here, which is the contribution of part of the molecule, right? So the log p of part of the substituent, and then you have the Hammett constant, right? You have the Hammett constant, and this one is your overlap of your graph, right? So what he gets is that activity increases if pi is positive, and then sigma is negative, right? So what you need for androgenic blocking activity is hydrophobic. So other compound yang tak ada hydrophobic substituent, yang tak ada electron donating substituent, ada compound yang tak cukup syarat tu, cross lah, right? Kita buang daripada kita punya list of candidates. So list of candidates kita akan jadi makin berkurang lah. Yang selepas you run Qsar model ni, you nampak daripada 1000 compound dia dah jadi 250, because yang lain-lain tu dia tak memenuhi dua syarat, right? Dia perlu dua syarat ni, right? Mesti pi is positive, mesti sigma negatif. Kalau salah satu tak ada, then keluarkan daripada you punya candidate. Okay, this is another example, anti-molar reactivity of phenytoin and Carbonyls kat sini. Right, so these are the equation. Kat sini tengok lebih panjang lah daripada yang original equation tadi. You ada pi dekat x, pi dekat y, sigma x, sigma y, and then last the log p squared lah. overall contribution. Hydrophobic increases, right? Parabolic equation implies optimal log P not value of activity. Activity increases for hydrophobic substituent, especially for ring Y. Activity increases for electron withdrawing substituent, especially for ring Y. Okay. So basically ring Y ni, you punya compound dekat ring Y, kalau you nak improve the Phenytoin hydrophobic and electron withdrawing substituent dekat ring Y, right? You boleh attach kat sini untuk improve dia punya anti-malarial activity dia. Right? That's basically what the Qsar model tell us, right? You need your compound to have substituent, hydrophobic substituent, especially at ring Y. You need your compound to have electron withdrawing substituent. Remember, all the compound, syarat dia, all the compound must be of similar scaffold, right? So kalau you punya asal ada phenytoin kat sini, then kena ada lah, kena ada lah phenytoin kat sini as the scaffold. Maybe you tak nak change the amino carbonyls kat sini, you tak nak change kat sini. Maybe you tak nak change kat sini, you just nak modify saja, right? You just nak modify. So you have like 50 options kat sini, you have like 50 options kat sini, and in total maybe 50 times 50 you get like 2,500 compounds. Bila you ada 50-50 kat situ, combination dia sama ada dia sama ataupun dia lain, and then you ada then you boleh screen out lah that from 2,500 tu, you boleh screen out, make sure that mesti apa tu, mesti requirement dia at least dekat yang Y ni mesti ada hydrophobic substituent and mesti ada electron withdrawing substituent. So this one that you can use to cancel out the substituent yang tak sesuai. Craig plot ni is a statistical method lah. Dia measure terus, combine terus dua-dua value tu, plotkan dia dalam Craig plot ni lah. So this is like a map lah. Okay. So kalau you ada Craig plot ni, it depends lah. It depends on your statistical method juga. Because you can use apa tu? If you plot one parameters against the other, then you need to find that one. If you want both of them positive, right? If you want both of them positive, then you look at this part of the top right lah. Right? Kalau you nak you punya apa tu plot you positive, then you go top right. Right? Kalau you nak salah pi dia negatif, sigma positif, then you go top left. Right? Kalau you nak sigma negatif dan pi negatif, you go top bottom left and bottom right. So kat sini dah identify dah compound kat mana. Okay. So quickly decide which analog to synthesize if the Hunch equation is known. Because you need to know from Hunch equation whether you punya sigma ni nak negatif ke nak positif. Kalau Hunch equation bagi tahu that sigma mesti negatif, then tak perlu tengok bahagian atas lah. Tengok bahagian bawah je. Craig plot ni. Kalau Hunch equation juga bagi tahu, then you need a positive pi value, then terus tengok dekat sini lah, bottom right. Terus ada tinggal berapa je daripada banyak dot ni, blue dot ni, kalau you punya Hunch equation bagi tahu minus sigma and plus pi, contoh kita tengok balik yang tadi. Mana tadi? Saya dah terlepas tu. Okay. So dia kata pi mesti positif, sigma mesti negatif. Contoh because from this equation you dapat, right? Pi kat sini positif depan dia, sigma kat sini negatif depan dia, negatif. So pi is positif, sigma is negatif. So pergi lihat dekat sini, pi positif, sigma negatif. Kat sini lah. So you ada 1, 2, 3, 4, 5 compound je. So daripada banyak-banyak dot ni, you tinggal 5 saja yang you nak proceed based on your Qsar model tadi lah. So that is yang guna Craig plot. Orang pakai top list method is more like macam binary method lah. Dia tukar 0 and 1, 0 and 1. Whether present ke tak present, present ke tak present. Okay. So top list method lah. Top list is a flow diagram series of steps directs the medicinal chemist to produce a series of analogs, some which have greater activity than lead, used to start the tree lah. Dia macam tree decision lah. Dia macam tree decision. So it can be used for aromatic and aliphatic lah. Okay. So tak berapa sangat lah yang ni dia macam ni. Dia tree decision method lah. Okay. So whether it has the same activity or it has more potent, more activity, or it has less activity. Okay. So these are how it reaches the decision lah. Yang mana paling bagus lah substituent. Kalau tengok kat sini Cl, CH3 basically you have Cl, tak ada banyak beza because equipotent maknanya lebih kurang sama and then you have yang more potent your substituent and maybe you tak perlu pergi sampai sini, maybe you terus tengok dekat more potent saja you can add F3 kat sini and then you change jadi 2,4Cl2, change lagi jadi 4NO2. It's based on whether dia semakin improve atau tidak. Kita nak dia semakin improve lah, improve dan improve. So dia semakin lama semakin ke bawah, right? So maybe dekat awal dia lebih rendah, tapi bila you tambah 2 methyl group, then dia improve dia punya activity. Maybe you tambah lagi 3 sebelah sini, and then tambah lagi, and then tambah amine group ke, depends lah. Right, it's a decision tree. It's quite complicated, right? And this is example for aliphatic substituent lah. Kalau tadi ni aromatic sama je cara dia, sama. It's a decision tree, right? Oh sorry, yang ini bukan binary. Sorry, decision tree. Yang ini binary. Free Wilson, yes. Free Wilson ni binary. Whether the substituent ada atau tak ada. Saya silap tadi. Okay. So an equation is derived basically guna Excel lah yang ni. Yang ni paling short boleh guna Excel lah, right? So you list all the substituent yang you ada untuk measure, or you can potential substituent yang you nak ubah dekat you punya parent compound tu, and then you guna value 0 or 1 dekat you punya sample. Sample dia whether substituent yang you nak tu ada tak dekat compound A, right? Kalau tak ada, kosong. Right, pergi pula compound B, whether substituent yang you nak tu ada tak kat compound B. Kalau ada, 1, ada macam tu, right? So and then you can measure its activity by summation of this value okay. So the contribution ni kita punya how big is the contribution lah. How big is the contribution? So this is another method lah. Ada kelebihan dia, ada kekurangan dia compared to the Hunch lah. Right? Yang famous ni Hunch lah tadi ni. Hunch equation ni. Right? And then you boleh guna Craig plot. Craig plot paling senang lah untuk you dapat terus identify which compound terus kat sini. Right? From Hunch equation, plot the Craig plot and then ambil je yang mana yang fit the Hunch equation punya requirement. Terus dapat. Kan? Okay, so the free Wilson, there are advantages. No need for physical-chemical constants or tables. Useful for structures with unusual. It's not true lah tables. Guna table senang ke? You ada list of compound on one column, and then you ada all the substituent in another column, and then you tak one because bila pakai Excel, in the end you just letak formula sama dengan sum yang semua substituent tu, dan terus keluar value basically. Best juga guna table. Useful for structures with unusual substituents because you tak perlu nak measure dia punya physical chemical constant lah, right? Useful for quantifying biological effects that cannot be quantified lah by Hunch method lah, itu je. Disadvantages dia, a large number of analog needs to be synthesized because we need to synthesize lah untuk dapat value K, right? Okay. It's difficult to rationalize why specific substituents are good or bad for activity, right? The effect of different substituents may not be additive. Contoh intermolecular interaction. Tapi kita kira dia punya equation is additive kan? Kita summation semua ni. Cuma sometimes maybe the effect tu bukan additive effect lah. Itu dia punya disadvantages lah. Right? Okay, again these are the properties descriptors tadi, right? Saya saja ulang je table ni tadi. Saya tunjuk awal tadi dah untuk contoh lah, right? So yang famous apa tadi? Log P ni, right? Pi, log P, sigma, tough ni, tough ni sebenarnya yang ini steric parameter ni, induktif ni jarang agaklah guna, right? Tough ni steric parameter ni lah. ES ni, so ES. Kalau you nak include computational calculation, you can do quantum calculation and calculate the HOMO-LUMO energy dia, electrostatic potential dia, right? Using software, you can calculate the van der Waals radius, calculate molar mass, calculate molar volume. You can use software for this. No need to go to the lab. Right? But for this one, for example, like partition coefficient, you can do calculation, but you need experimental data as well. Okay. This one is super delocalizability. Ada juga. Okay. So this is an example of molecular descriptors. Okay. Baru nak masuk, dah habis lecture. Okay, saya nak stop recording.
Recording stopped.
Okay. Any question before I summarisekan hari ni punya lecture? You have any question? Berkenaan Qsar ke, berkenaan methods ke? Ada? Ke semua dah lari dah? Ada lagi tak kat sini? Anyone here? Ada lagi? Ada orang tak?
Ada.
Yang dekat college slow doktor.
Internet kat college slow?
Doktor.
Ayo. You all akan kuliah online sampai habis semester kan? Kuliah memang online sampai habis semester, betul tak?
Betul.
Saya tak boleh guna whiteboard lah. Saya tak boleh lah. Saya kalau mengajar saya guna whiteboard lah. PowerPoint saya guna juga, tapi kalau ada whiteboard senang. Bila pakai komputer dia jadi slow sikit. Yalah, internet biasalah tu. Wi-Fi college Wi-Fi apa? U-Spot tu Ke kalau pakai mobile data pun tak okey juga.
Mobile data tu ikut tempat jugalah. Kalau kat bilik saya ni macam ada slow untuk data saya.
Apalah. I think I ada record tadi. Maybe nanti I share lah recording kalau you nak go over balik lecture tadi kan. But for now I just I nak summarize sikit lah pasal Qsar ni, what I talk just now. First, you kena faham yang Qsar ni basically is a statistical approach. Itu you kena faham dulu mula-mula lah. Statistical approach, and then dia digunakan untuk screening, right? So you have a haystack, you want to find a needle, you reduce the hay. Right? You want to reduce the hay so that you can easily find the needle, right? So itu gunanya Qsar. Itu yang paling fundamental use of Qsar is basically just to make our life easier lah, of course lah kan, untuk reduce cost and reduce time. Tak perlu nak synthesize semua compound, tak perlu nak test semua compound. You can just have your Qsar model and feed all your compounds, yang list of your compounds into the model. But first, you need a list of compound. To get a list of compound, first you need an original compound, a base compound, right? And then that base compound juga mesti dah tunjukkan biological activity. Itu dulu. Contoh contoh daun bunga raya. Sup ketam boleh buat baik demam, kan? So apa ada dalam sup ketam? Okay, maybe ada molekul A ni yang kita interested untuk tengok whether dia boleh induce something that can relieve the fever, right? So you have that kind of compound. Or or maybe in natural product, right? Kalau yang buat FYP yang buat natural product tu, you dah apa untuk lidah buaya, boleh baik luka, kan? So then what is the compound in lidah buaya? You pun masuk ke lidah buaya tu, you refract everything, you dapat dia punya compound, and then you test, synthesize, you tengok, oh yes, ada effect on the activity. But that is a natural product. Now you want to synthesize a compound that is similar to that, yang sama macam compound yang you dah test dekat lab tadi, yang you dah dapat result yang memang confirm dia ada biological activity. You nak improve lagi, right? Nak improve lagi supaya bila you makan je ubat ataupun you letak je compound tu, luka terus baik. You nak macam tu, right? So in order to do that, you need to find similar compound to that compound, to that base compound yang mula-mula tu. Dia mesti similar, dia mesti ada properties yang dia sama. And then maybe you ubah-ubah, you find dulu compound yang apa tu ada dalam database lah, maknanya ada, memang ada compound yang sama macam compound tu. And then kalau tak ada pun, you modify that compound. So macam de novo design lah, you modify, you tukar dia punya substituent ke apa ke tadi, and then you have this vast list of compounds, and then you build your Qsar model, right? You build your Qsar equation, and then bila you dah ada Qsar equations, you can use Hunch equation for initially, untuk mula-mula you pakai je Hunch equation yang mula-mula tu, yang mula-mula dia buat tu, log p squared plus log p plus pi sigma and es, and then you pakai yang itu je, and then as you get more and more compounds, you can add more and more descriptors. Kalau you nak dia punya tu lebih spesifik, you kena add descriptors lagi. Dia semakin banyak you tambah dalam equation tu, semakin banyak descriptors you tambah dalam equation tu, semakin cepat list tu akan reduce, right? Tapi kena jaga-jaga jugalah, because bila you tambah terlampau banyak juga, kadang-kadang dia result dia terus kosong, because sometimes kita are being unreasonable, right? There's no way that a compound that has 5 oxygen can have high log P values, for example, something like that, right? Janganlah require at least 5 oxygen, but must have high log P value. Tak kena lah, dua tak kena, right? Bila dah terlampau banyak oksigen tu, dia akan basically akan jadi macam lebih hydrophilic, so log P dia akan confirm rendah, right? So kena reasonable juga, right? Bila kita build kita punya Qsar model, apa-apa pun kita check kita punya Qsar model, whether kita punya linear regression tu, bila kita buat regression plot tu, kita dapat tak R squared tu close to 1, right? Bila you dapat R squared tu close to 1, meaning your Qsar model is good, then you can add more compounds to your test set, right? You ada training set, and you train dulu untuk check you punya Qsar model. Bila you dah dapat Qsar model dan yang sangat bagus, and then you boleh add more compounds to test, and then basically in the end what you want to achieve is that you have a set of few compounds, right? A set of few compounds that according to Qsar would be very good or produce very high biological activity. Itu yang you nak in the end. Okay, you can include docking as well, right? You boleh include docking, tak ada masalah. Kalau you rajin nak dock semua. Okay. Ataupun you train sekarang ni, I think maybe next lecture ada kot explain tentang machine learning. Sekarang machine learning lagi cepat kalau you nak buat Qsar ni, because you dah ada machine learning. Kalau macam 3D Qsar tu, dia dah guna artificial ANN tu, artificial neural network, dia dah pakai ANN, then semua jadi lebih ni lah. And remember, we have software to do this. That's what itu yang saya selalu suka ingatkan student. Walaupun you rasa it's a bit complicated, not yet actually. Ada lagi yang lebih complicated dari ni. But in the end, when it comes to application, there's already software for this, right? You can just choose je nak masuk parameter apa. Oh, I nak atomic charge, I nak electrostatic potential, I nak molecular weight. You just klik. Kalau ada dalam database, value semua terus keluar. And dia terus keluar dia punya C log P value. right? Remember C log P, calculated log P kan. Kalau dah ada dia punya log P dalam database dia tu, dia ada dia punya apa, for every atom tu ada dia punya log P dia, then you can add je, summarize, summation semua kan, sum everything, and then komputer tu keluar, you tak perlu buka calculator pun, right? Usually software buat semua benda ni, right? But it needs to run something lah. Kena ada juga apa yang you bagi ya. Software dia macam dia tak tahu apa. Dia apa yang you bagi, arahan itu yang dia buat, right? So the arahan tu, instruction tu must be the correct instruction lah. And you have to check lah. Always check, check the R squared and so on. Okay, untuk dapatkan apa tu Qsar model yang bagus. Right? So ada biological activity yang you nak tengok, you dah ada standard synthesized compound, and then you generate a list of test compounds, and then model the Qsar equation, right? Model the Qsar equation, test, validate your Qsar model. Qsar model tadi validate supaya R squared dia ataupun linear regression dia tu bagus, semua dia equation tu bagus, and then identify which compound that satisfy the equation, right? That compound yang daripada list yang banyak-banyak tu. So basically what you that process is basically a screening process. Okay. Kalau ada soalan boleh tanya. Kalau tak nak tanya voice boleh chat pun boleh. Tak ada masalah. Okay. Ada. Attendance jangan lupa. Yes. Apa dia tu?
No question, Doktor.
Location?
No question, Doktor.
No question, okay. Line saya pun tak okay lah. Dengar. Alright. Okay, kalau tak ada.
Saya rasa line saya yang tak okay.
Alright. So I'm going to continue lecture again on Monday lah. Monday kita kelas berapa? 12. So I see you again on next Monday, right? At 12. Okay. Thank you everyone. Bye.
Thank you, Doctor.
Thank you, Doktor.
Thank you, Doctor.
Thank you, Doktor.
Welcome.